Okay, so now we're going to state a theorem called Spectral Decomposition Theorem for Hermitian matrices. So this theorem is very useful for specifying orthonormal bases for measurements. But before we state the theorem, let me remind you that a matrix, so take a matrix D, it's an n by n matrix. So we say that D is a diagonal matrix if and only if the only non-zero entries of D are the diagonal entries of D. Okay. And it's all zero elsewhere. Okay, so a diagonal matrix is something like, so it's non-zero on the diagonals maybe something that looks like this, and it's all zeros elsewhere. Okay. Okay, so the spectral decomposition theorems, it goes like this. So this is spectral decomposition theorem for Hermitian matrices. There are many other versions, but we are interested in for Hermitian matrices, spectral decomposition theorem. So the theorem says that if A is a Hermitian matrix, then there is a decomposition of A in the form of, so A can be written as Q lambda Q adjoint, okay, where Q is a unitary matrix it's a unitary matrix whose columns are the eigenvectors of A, okay, and lambda is a diagonal matrix whose entries are the eigenvalues associated with the eigenvectors. Containing the eigenvalues. Okay, so in other words, it says that every Hermitian operator A on a finite dimensional complex vector space V can be represented by a diagonal matrix whose diagonal entries are the eigenvalues of A and whose eigenvectors form an orthonormal basis for V. Okay, and we call the set of bases an eigenbasis. Okay, so ultimately Hermitian operators and the spectral decomposition theorem are really just mathematical formalisms for specifying orthonormal bases for measurements. So it's a fancy way of stating or specifying orthonormal basis states for our measurements. So recall that from the earlier video, we gave the intuitive treatment on measurements. We said that it was just a projection onto one of the basis states. Well, now we're giving the mathematical formalism behind the measurement process. Okay, so for a given quantum state and for a given observable, we want to define, well, we just have to define a set of orthonormal basis states for our measurements. And the outcomes will be the eigenvalues of that observable. Okay. Okay, so if we are given a general state, psi, say alpha 1, phi 1, alpha n, phi n, measuring a Hermitian matrix on psi, so A is an observable here, a Hermitian matrix. We're actually measuring the observable. We're not measuring psi. We're measuring the observable A on the state psi. Okay, so just to be correct with the terminology, on psi. So this is just a projection onto one of the eigenvectors of A. Okay, so the outcome of the measurement will be one of the eigenvalues of the observable A. So outcome one of the eigenvalues of A. Okay, so say lambda j. Okay, and we obtain lambda j with probability magnitude alpha j squared. And then the system will be left in state phi j. Okay, so the new state of the system will be the corresponding eigenvector of the measured eigenvalue. So this is how the measurement process works. So let me give an example to make it more concrete. Okay, so suppose that we are given a state psi alpha 0 plus beta 1. Okay, so suppose that this is a single qubit system, and suppose that we have an observable x. And the observable is defined as 0, 1, 1, 0 matrix. Okay. Oops. Okay. So then we need to determine the eigenvalues and eigenvectors of x. Okay. And they're quite straightforward. The eigenvectors of x, okay, well, the first one is v1. It's actually ket plus. So it's 1 over square root 2, 1 over square root 2. This is ket plus actually. The second eigenvector is, let's denote it by v2, and it's ket minus. So 1 over square root 2 minus 1 over square root 2. And this is ket minus. And the corresponding eigenvalues will be, let's call them lambda 1 and lambda 2. Lambda 1 is equal to 1 and lambda 2 is equal to minus 1. Okay. So as an exercise, you may verify these. So how do we make the measurement itself? Well, we first need to write psi in the bases of the eigenvectors of the observable. So to make the measurements, we need to write psi in the basis of v1, v2. Okay, so these are the eigenvectors of the observable that we want to measure, and we want to measure x on psi. Okay. So remembering what ket 0 and ket 1 is in the sign basis, psi is simply alpha plus beta divided by square root 2 ket plus alpha minus beta over square root 2 ket minus. Okay, so psi can be written in the sign basis like this. Now, when we make a measurement on psi, the outcome will be either 1 or minus 1. Okay, because those are the eigenvalues of the observable. So we get 1 upon measurement So we're measuring x, we're measuring the observable x on the state psi, and we get the eigenvalue 1 with probability what? With probability magnitude alpha plus beta divided by square root 2 squared. Or we get the other eigenvalue, minus 1, with probability magnitude alpha minus beta over square root 2 squared. Okay. And so in the case that if we get 1, the new state of the system will be the corresponding eigenvector, which is ket plus. But if we get minus 1 as the outcome of the measurement, then the corresponding eigenvector will be ket minus, and this will be the new state. Okay? So this is how measurement works in quantum computation. But what if we have repeated eigenvalues? That might seem like a problem at first, but it's really not. Suppose that we have a three-dimensional vector space, for example, okay? So assume that we're given some Hermitian operator A, okay, and suppose that the eigenvalues of A are maybe lambda 1, lambda 2, and lambda 3, and the corresponding eigenvectors are phi 1, phi 2, phi 3. Let's denote them by the ket notation. Okay, and assume that lambda 1 equals, say, lambda 2. Now what do we do in this case? Well, this is no problem because linear combination of phi 1 and phi 2 is still an eigenvector of A with the same eigenvalue. So we can collapse this two-dimensional vector space into a two-dimensional space. Okay, we can do a reduction on the vector space. Okay, so this should be no problem. Okay, so now let's generalize this procedure, and let's generalize this formalism. Now we want to generalize the definition of observables for measuring in an arbitrary basis. Okay, so let's generalize this so as to make measurements in arbitrary basis states phi 1 up to phi n, let's say, with arbitrary real outcomes lambda 1 through lambda n. And we do this by density matrices. So if we want to project a state onto another state, we do this by projection matrices or density matrices. Now if we want to project a state psi onto another state phi, we can do this by density matrices. We use density the density matrix. Let's say we use density matrix ket phi and bra phi. Okay, this is called a density matrix, also called a projection matrix. Now, we already know ket phi, but what is bra phi? So this is actually the dual of ket phi. It's called bra phi, and bra phi is simply the adjoint of ket phi. Okay. So verify this. So given psi, p psi, as a matter of fact, projects psi on the state phi. Okay, for some complex number c. Why? Well, let's shortly actually show this. So p times psi will be equal to, so p is ket phi bra phi times psi, right? So this is the inner product of phi and psi, so it's just a scalar value, right? It's some complex number. So we have some complex number times phi then, right? So as mentioned here. Okay, so let's generalize this. Given an orthonormal set of vectors, let's call them phi 1 up to phi n, and a set of eigenvalues lambda 1 through lambda n. The corresponding observable then for these eigenvectors and for these eigenvalues is simply the corresponding so it's simply summation lambda I and the density matrix phi I bra phi I. Okay, so this gives us the mathematical formalism behind measurements and observables. Okay, so this is just a fancy way of explaining the intuitive notion behind projective measurements that we've mentioned in the previous video. So as a postulate, we can state that this is a postulate of quantum mechanics for measurements. So what's a measurement? What's an observable in quantum mechanics? Well, they correspond to Hermitian operators. Okay. Measurement postulate. To each physical observable of a quantum system there corresponds a Hermitian operator. Okay, so this is our postulate, our measurement postulate. So in classical physics, we usually assume that measuring a system would leave the system in the same state, that the measurement wouldn't destroy the state of the system. Okay, but this was shown to be wrong in quantum mechanics. Observation of the system may collapse the state of the system. So it doesn't leave the state of the system same as earlier. Measuring the system might yield another state. It doesn't preserve the state of the system. Okay, so although in classical mechanics and classical physics this is not the case, but in quantum physics, performing measurements on quantum systems may change the state of the system. Okay, so observables can be thought of as legitimate questions that we can pose to quantum systems. Okay, and each question admits a set of answers, and those are the eigenvalues of the observable. So when we get to measure an observable, we get one of the eigenvalues of the observable. Okay, and the new state of the system will be the corresponding eigenvector associated with that eigenvalue. Okay. Okay, so now that we've explained measurements and observables, we've pretty much covered all about the basics of quantum mechanics. But we should also talk about the EPR paradox and quantum gates in the next video. So you can find more details in the lecture notes. Just send me a message, and I'll give you the link. So I'll see you in the next video.